Thank you all so much for joining. We are getting started now. We would like to start by introducing our president, Eric Isaacs. So Eric, please take it away.
Institution for Science. And it's really a pleasure to welcome all of you to this first installment of our new digital programming series. Last month, as we were postponing our public talks across the country and had to ramp down on campus research, we thought a lot about how best we could stay in touch with all of you. So we've decided to create this virtual series to share our ongoing work and to help you stay engaged with some of the exciting discoveries that are happening here at Carnegie. So over the next few weeks, Carnegie Science researchers from multiple disciplines will present on topics ranging from astronomy to global ecology to microbiology. You'll get a chance to learn about the inner workings of telescopes, explore the secrets of the world of microscopic organisms that live inside of each of us. So I hope you will join for these conversations as we gather virtually to learn about the many ways Carnegie scientists are improving our understanding of the cosmos, of our planet, and of life itself. So now I have the distinct pleasure to introduce our first speaker in this series, Dr. John Mulchaey, who is the Crawford H. Greenewalt Chair and the Director of the Carnegie Observatories. John is known throughout the world for his work on groups and clusters of galaxies. And these systems present amazing opportunities to study processes that shape the formation and evolutions of galaxies and, in fact, our universe. Early in his career, John and his research team revolutionized our understanding of galaxy groups by revealing the existence of large amounts of dark matter in their composition. And more recently, he joined in the discovery of the first known binary quasar system. John earned his Ph.D. from the University of Maryland, and he joined Carnegie Observatory staff in 1999 and was ultimately appointed in his current position of director in 2015. So please join me in welcoming my esteemed colleague, John Mulchaey. John?
Hi, everybody. Let's see. Thank you for joining us. As Eric has said, this is our first attempt at doing this. Let me actually, oops, hold on. Am I heard? Let's see.
Yes, thank you, John.
Oh, sorry. Thank you. I'm sorry. I want to first apologize because I had some technical difficulty actually getting into the Zoom. And so that's why we're a little late today. So I'm just a tiny bit frazzled, like everybody. But I do really want to thank everybody for joining. It's amazing. I see we have over 400 participants. This is really, really great. And so it's a little strange to give a talk without being able to see the audience. So I'm going to plow forward. But we do hope if you have questions, you will feel free to ask them, given the little Q&A at the bottom of the screen there. And so today I thought I would talk about, let's see, my favorite topic, which is really the Hubble Space Telescope deep sky images. Many of you who've heard me give talks before know that this is really, these images are really my favorite in astronomy. I say that over and over again. And I thought this would be an interesting time to kind of just dive in and talk about why they're so important and what we've learned from them. And let's see, so with that, let's see, I am sharing my screen, right? Here we go. Hopefully everybody can see my, Michelle, can everybody see my screen?
I can see your screen, thank you.
My slides? Wonderful, excellent, okay. So I'll talk a little bit about what these Hubble Deep Field images are in a second, but first let me just remind you a little bit about the Hubble Space Telescope. So the other reason I thought this would be an interesting time to talk about Hubble is it's coming up on its 30th year anniversary later this month. And so that's kind of exciting. It's really, I was a young graduate student at the time when this was just getting launched. And so it's remarkable to think it's been 30 years since this telescope has been around. But just to tell you a little bit about the telescope itself, can you guys be quiet? Sorry, I have a couple dogs who decided all of a sudden, maybe there's a squirrel in the yard. I'm sure we'll be visited by them. They keep Zoom bombing all of my talks I'm trying to do anyways on Zoom. But the Hubble Space Telescope isn't really the biggest telescope ever. It's kind of a small, ordinary telescope in some sense. It's only 2.5 meter or 100-inch mirror. But what's interesting about the Hubble telescope is, of course, that it's in space. It's in low Earth orbit. And so this means it's above the atmosphere, which means that, and the atmosphere, of course, is a problem for us here on the surface, astronomers at least, because it blurs our images. This is what causes stars to twinkle, for example. And so the Hubble Space Telescope being above the Earth's atmosphere doesn't have that problem. So the Hubble is able to deliver really the best image qualities we can get. And that's really been its primary benefit to astronomy as we know it. Now, I like to think of the Hubble as one of the 3 most important telescopes ever launched, or ever put in use, just to kind of give you an idea of just how important it really is. The first, I would argue, would be Galileo's original telescope, which he used to show, in fact, that the sun was at the center of the solar system. He did this by, for instance, looking at the moons of Jupiter. He realized they were orbiting Jupiter and not the Earth. So that kind of got rid of the old geocentric model of the solar system. The second telescope that I would argue is important was, of course, the Mount Wilson 100-inch right here above us in the hills of Los Angeles. 100-inch was so important because this is, of course, where Edwin Hubble did his amazing work. Edwin Hubble, as most of you probably know, was, of course, a famous Carnegie astronomer. And Hubble in the 1920s had 2 really remarkable discoveries. The first was, I like to say, he effectively discovered the universe. What he did was he showed for the first time that there were galaxies beyond the Milky Way, which is what I'll talk about today. And then, of course, 5 years later on, he had the results that really led to our understanding of the universe was expanding. And so the Hubble Space Telescope was named after Edwin Hubble for that. And then the Hubble is the 3rd most important telescope in a sense, because what it has done, and that's what I'll talk about now, is it's really allowed us to understand how the universe has changed over time in truly remarkable ways. But before I do that, I just thought I would, of course, remind you and show you some other beautiful images from the Hubble Space Telescope. There are many areas of astronomy that Hubble has played a huge role in. These are just 4 of my favorites that I picked out there. On the upper left, you see a star-forming region in the Milky Way galaxy. What you're really seeing is you're seeing a gas cloud that's being eaten up by radiation from young stars. And so you see these beautiful pillars of light there. That's really one of my favorite Hubble images. On the upper right, you see the merger of 2 galaxies. This is the Antennae Galaxies. And of course, these are really interesting because this is a process that many galaxies, including our own Milky Way, will eventually go through. And for those of you with a good memory, you'll remember now, 26 years ago, it's been, Jupiter got bombarded by comet Shoemaker-Levy. It hit in multiple pieces. The comet broke up and then hit Jupiter. And with Hubble, we were able to actually see the damage, so to speak, on Jupiter. And you see that kind of round, round spot there. And that's actually where one large piece of the comet actually impacted the planet. That was really kind of a very rare event and one we were really lucky to have when the telescope was up. And then in the lower right there, I have an image of a deep cluster of galaxies. And this is an area that I've worked on quite a bit. What's interesting about these big massive systems is they are really the most massive systems in the universe. They're really great probes of dark matter particularly. And that's where Hubble's images of these systems have really helped in that realm. But really, so even though Hubble's had an impact on many fields of astronomy, really its most important contribution is for understanding how galaxies evolve over time. And so just to kind of remind you of what a galaxy is, this is an image of what I think most of us have in our mind when we think of a galaxy. This is a beautiful spiral galaxy. This is what the Milky Way would look like if you could step outside and kind of look back at it. And what you're seeing there is the light of 200 billion stars, about 1 trillion planets. About 95% of the mass of this galaxy, of a galaxy like this one, would be in the form of this mysterious dark matter that we still don't understand. And of course, it was our famous Vera Rubin, a Carnegie astronomer, who of course first showed that galaxies were dominated by dark matter. And at the bottom, I put a little scale there. A galaxy like the Milky Way is about 100,000 light years across. So a light year is a pretty big distance. It's about almost 6 trillion miles, to put it in perspective. So these are really large and immense systems. And it was, as I said earlier, Edwin Hubble was the first to kind of show that, that systems like this existed. Now, when we look at the local universe, even though we often think in our minds of these spiral galaxies, Hubble was one of his other big results, in fact, was noting that galaxies come in different sizes and shapes. And so on the left, these are kind of the three categories where we would normally classify all local galaxies. On the left is the spiral galaxy, like the Milky Way. In the middle there is what we call an elliptical galaxy. And these elliptical galaxies obviously don't have that beautiful spiral structure. They're more football shaped is the way to think about it. And they only contain mostly old stars, where the spirals and the other class irregulars have a lot of younger stars. And there's an important clue there, which we'll talk about a little bit when I get going. The third class are things that are called irregular, which, as the name suggests, they don't fall into one of these other two categories. They have kind of unusual shapes. And those of you who've been to the Southern Hemisphere and have seen the Large and Small Magellanic Cloud, those are nearby examples of irregular galaxies. And they tend to be blue, actively forming star systems. So they're quite interesting, as the Large and Small Magellanic Cloud are. So anyhow, locally, this is kind of when we look out what we would see. But what Hubble has done, the Hubble Space Telescope has done, is it really has allowed us to understand how the universe went from a big bang to forming these beautiful structures that we see locally. And the way we do that in astronomy is by looking back in time, looking at objects that are further away. And so we're seeing what they look like in the past. And as a class, one can try to study, for instance, how did spiral galaxies change over time? I hope you are all still there, because I just got a thing saying your internet is unstable. I'm going to assume everybody's still there.
I'm still here.
Because now we get to the actual fun. Okay, good. That was a little scary message to get. Fun times we live in. Well, how has Hubble played a role in understanding galaxies? Well, that role has primarily come from these very, very deep images like the one you see here. This one is called the Hubble Ultra Deep Field. This is really the deepest image that we've ever taken with the telescope. And it's a truly remarkable image. This is the one I often refer to as my favorite image of all time, for obvious reasons. It's just so incredibly beautiful. But there's just such amazing scientific content in this image. So, well, let me just first of all say, well, what is this image? Well, this image is basically 23 days worth of exposure to the Hubble Space Telescope. Basically, we pointed the telescope at a single area on the sky and integrated away for effectively what ends up being 23 days worth of exposure. That's extremely long exposure with any telescope, but particularly with the Hubble. And just to give you an idea of just how small on the sky this area is, the center of this field is called the Extreme Deep Field, or XDF for short. And on this diagram here, you see that little box in the center called FDF. That XDF, that shows you the size of this field relative to the full moon. This is a really tiny patch on the sky here. And in fact, you would need about 30 million of these patches if you wanted to cover the entire sky. So this image, this Hubble Ultra Deep Field, is just a small glimpse into the universe, but a really important one. So, well, what are you seeing here? Well, what you're seeing here, of course, distant galaxies. In this particular image, there's less than a handful of things that are not galaxies. There's a few nearby stars in the Milky Way, but almost everything you see in the image is in fact a distant galaxy. This image alone has 10,000 galaxies. I mean, it's just it gives you a sense of just how tremendous the universe is in terms of size. And if you extrapolate around the sky, you would have approximately somewhere like 1 trillion galaxies total in the universe. A really, really incredible amount of objects. So the other thing you'll notice here, though, when you're doing a deep integration like this and you point the telescope at a single location for such a long time, is you're getting objects at different distances from us. And so this next diagram kind of gives a nice display of that, where we've basically taken all the galaxies in that image and put them in 3 different boxes here, depending on how far away from Earth they are. And so on the far left, you see there's just a few objects that are nearby. And by nearby here, I mean less than 5 billion light years away. It's not very nearby. To put that in perspective, the Earth is a little less than 5 billion years old. So those galaxies, that light we're seeing left them around the time the Earth was forming. The middle patch there shows you kind of most of the objects, the bigger objects you see on the image are in the range of about 5 to 9 billion light years away. And then on the far right, you see the most distant objects, the smallest things, which tend to be 9 billion light years away or further. I'm sorry, I'm laughing because my dog is scratching. Why are you scratching? Anyhow, so what you see in this deep image is you're seeing galaxies over a range. And so as astronomers, if we want to understand how galaxies have changed in time, you can study the populations in bins like this, and you effectively can see how they have evolved through that time period. Now getting back to this, the image itself, you'll note that there's a lot of information visually one can get from just looking at the image. One is you'll see that, of course, there's a lot of variety in sizes and shapes. And this similar to the local galaxies. In fact, you see some objects that look somewhat like the Milky Way, kind of spiral looking blue galaxies. You see some objects that are kind of more elliptical shapes, those ones that you see the reddish that tend to be red in this image. But you'll notice that the colors of those are also very different. And so I wanted to spend a few minutes to talk about the colors, because the colors are extremely important. The colors you're seeing in the image are reflecting different types of stars. So when we know from our studies of stars in the Milky Way and the Large and Small Magellanic Cloud that the hottest stars are blue stars. They're the most massive stars. They burn extremely brightly, but they burn themselves out very rapidly. And by very rapidly in astronomy, I mean millions of years. So a typical blue star will only live a few million years or 1,000 million years, something like that. That's a really short time scale for astronomers. A red star is quite the opposite. A red star is much cooler. They tend to be lower mass, and they tend to burn very slowly. And so a red star can live for tens of billions of years. And stars like the sun, which are yellow, are kind of in between. And so if you imagine a galaxy forms, and it formed we think when stars form, they form all these stars kind of together at the same time in a cloud. So you imagine a galaxy forms, and you form the blue stars, the yellow stars, and the red stars all at once. Well, if you don't continue to form new stars, after millions of years, the blue stars will all die off, leaving you just the yellow and the red stars. And then eventually the yellow stars will die off and you're left with the red stars. And so in this image, when you see the colors, you actually can learn something just from the colors about the types of stars that are in a galaxy. So you'll notice that the things that look mostly like spirals, there's a couple near the top there in the middle, they look very bluish. That means those are systems that are actively forming new stars because they have a lot of blue stars. That means, and once again, actively means over millions of years, the last few million of years. Where the red ones you see are systems that apparently are no longer forming stars, because in those cases, it appears that the blue stars and the yellow stars have largely died out. Anyhow, so this image has all that information in it. What you learn from looking at an image like this is it's incredibly diverse, and galaxy evolution, or the understanding the processes involved here, is extremely complicated. So now I'm going to dive a little bit further. So if you add to the Hubble Space Telescope data by the original ultra deep image I showed you, if you, for instance, take observations in the infrared and you try to add, these are, oh, one more thing, sorry, let me go back. This is an important point because I want to make this, because I never talk about this. When you see an image like this, you may be wondering, I've just described how the colors are important. How do we know, are these colors real? And the answer, the way you actually find this is we do take these exposures with specific filters. So for instance, we have a filter in the Hubble Space Telescope we can put in that will basically eliminate all light except red light. And so you basically can get a red image. And you can do the same in a blue band or a yellow band. And so by taking these images in different bands, you can combine them to get something that is real, kind of realistic. So in fact, your eye, if it looks at this image, would see something very similar to this. Not exactly, but pretty close. So in this case, the colors are not fake, because people often ask me that when you see images, are the colors real? They really are real in an image like this, in that sense. Sorry, that was a little side thing I forgot I wanted to mention. Okay, now back to this. So some real exciting work once these deep fields came out happened in 2009 when we had an upgrade to the Hubble Space Telescope and a new instrument came online that allowed infrared observations to be added. So infrared are just other colors. These are cooler colors. And by adding these colors in, you could learn even more. And this is some work that Ivo Lebay, who was a Carnegie Fellow at the time when he did this work, and he's now a professor at Swinburne, has done. These are really incredible. What he's done by adding this infrared, he was able to find very, very faint galaxies that are in fact more distant than any of the other ones that you see in the image initially. And the galaxies you're seeing in this image are more than 13 billion light years in the past. So you really are seeing systems very soon after the Big Bang had happened. And you'll see their little blowups are quite nice here. All of these galaxies are very, very blue. And what that means, as I've said, is the blue stars means they're actively forming new stars. In fact, these systems are forming stars at an incredibly rapid rate that we never see in the local universe. And in fact, these are really the first star kind of systems that are forming. The interesting thing about these galaxies is they're not like the Milky Way is today. What you're seeing here are really tiny. These small systems are about 1% the mass of a galaxy like the Milky Way. And they're only about 5% of the size of the Milky Way in radius. So these are incredibly small objects. These, in fact, aren't really galaxies in the sense of galaxies today. These are, as I like to say, these are the seeds for future galaxies. Because this is the beginning. This is how you form these galaxies. You start with these small pieces of really active, very, very active star formation regions. And you'll even see their shapes. Their shapes don't look like ellipticals and they don't look like spirals. In fact, they look somewhat like the irregulars. And so in fact, what you're seeing is you're just seeing the start of galaxy formation here. This is really exciting. Over time, these galaxies, since this time, this data, when we're seeing them how they were 13 billion years ago. They would have since grown up and evolved into more full galaxies, we think, but that's the process we really have to try to understand. Now, Ivo did some further work with Eric Persson, who was a staff member at Carnegie who recently retired. And Ivo and Eric added to the Hubble Space Telescope using data from the ground-based Las Campanas Observatory. And the advantage of Las Campanas is we can go very, very deep because our telescopes are bigger than the Hubble Space Telescope. And so they used an instrument that Eric built called 4STAR, and they added this information in. And when they add this information in, they found a whole different class of objects in the early universe. These galaxies are about the same. They're about 13 billion light years away again, like the blue ones I just showed you. But these galaxies are intrinsically red. This means that they've already kind of died. And this is really interesting and unexpected because we expect in the early universe, there was a lot of gas around. And so star formation should have been very rapid, like we saw in that the ones that Ivo found previously. Those systems are kind of what we expect to happen because there's a lot of gas that stars form from. These galaxies are red. So they formed and somehow almost instantaneously stopped forming stars. And this was really not expected. And it was initially very difficult to understand because in that early universe, as I said, there should have been a lot of gas to form stars with. So what's going on? Well, our best guess is that these galaxies have been impacted by what are known as supermassive black holes. So a black hole is an object with such strong gravity that nothing can escape it. A supermassive black hole is one of these objects, a very special type of object that occurs only at the centers of galaxies. And these are, as their name implies, supermassive. These are 1 million to 1 billion times the mass of the sun. And so these are really giant monsters kind of sitting at the centers of, we now know every big galaxy. And so we don't fully understand why every big galaxy has one of these, but there's some important relation between galaxies and these black holes. But what can happen in one of these cases is as material kind of swirls in towards the black hole, the gravity is so strong from the black hole that this material heats up to extremely high temperatures. And rather than emit a lot of visible light like a star does, it actually emits a lot of X-rays. And so what happens is these black holes, if they're feeding enough and eating enough material, they can actually, the region around them can actually produce a very strong wind. And we believe this wind can actually blow up a galaxy in a sense, or blow out its gas, or prevent new gas from falling in. And if you stop the gas flow into a galaxy, then you have nothing to form new stars with. So our best guess is that these supermassive black holes are responsible for stopping star formation in these galaxies. Well, do we know these black holes exist? Well, of course they must exist because I wouldn't talk about them, but let me show you how we know that they exist. So going back to our Hubble Ultra Deep image, here it is again. When you look at this image, I just want to emphasize what you're seeing are stars. You're seeing the stars in the galaxies. And this is because almost all stars, including stars like the sun, of course, emit most of their light at visible wavelengths, which you would see with your eye. And so when you do a visible image like with Hubble, you really are just looking at the stars in the galaxies. If you take the same region of sky and you point an X-ray telescope at it, and this is something we've done, and this is a project I've worked on quite a bit, this X-ray telescope is called the Chandra X-ray telescope. It's effectively the Hubble for X-rays. It does very high resolution imaging. It's a space telescope, but in X-ray band. Now, when you look at an X-ray image of the same field, what you see here are not the stars, because the stars don't produce very much X-ray emission. So they effectively are invisible at X-ray wavelengths. What you see instead are these feeding black holes, the material swirling towards the black hole that's heating up and producing this very bright emission. And so an X-ray image like this is just showing you that there's a lot of black holes in the same field where we just saw a lot of the stars. And here the two are, so this is the same field now in X-rays and optical visible light. And if you do a detailed analysis, what you find are that the X-ray sources on the left are all associated with the centers of galaxies on the right. And this isn't surprising. This is telling us that these, in fact, supermassive black holes are at the centers of many of those galaxies. This is one way we know that, in fact. And so this is interesting. This means the universe has a lot of these accreting black holes. So maybe these black holes are responsible for shutting down star formation in some galaxies. But the challenge is, if in this image, the X-ray data, most of the black holes you're seeing there on the left are at those, I'll call them nearer galaxies. They're not really near. The galaxies that are maybe 10 billion light years away. We're not really seeing these X-ray black holes all the way back to the 13 billion years where we found saw those other galaxies Evo was studying. But so the question is, how far back do black holes even exist? And when did the first black holes appear? And so many of you, of course, who've heard me talk or who've heard or kept up with our press releases for the last few years know, in fact, that we have the world's expert on searching for black holes was a postdoc named Eduardo Benedos. Eduardo has now just moved on. He's moved on to Germany, where he is now a permanent staff member there in Germany. But Eduardo is the world's expert on looking for these black holes in the early universe. He's found more than half of the ones known. And he found the distance record in terms of the oldest one, which is over 13 billion light years away. And this he found using our Magellan telescopes at Las Campanas. And so this is really quite interesting. The black hole that he found that's 13 billion light years away, or we're seeing it 13 billion light years ago, that black hole is already 1 billion times the mass of the sun. And it's a bit of a challenge to understand how such a giant black hole formed so soon after the Big Bang happened. But it exists, so it means the universe knows how to do it. And what it means is that black holes really are potentially a source for taking galaxies and stopping star formation in them. But the challenge there is that it's, of course, much more complicated than what I just described, because we know some galaxies, like the Milky Way as an example. The Milky Way is about 13 billion years old too, we believe, and it's still forming stars after 13 billion years. So why did some galaxies stop forming stars within the first billion years of the universe, and others like the Milky Way are forming it for 13 billion years? All these galaxies have these giant black holes. We know that our own Milky Way has a supermassive black hole in it. So why did we escape and why didn't others? And I think this is one of the challenges for the next generation telescope, is to try to understand that and understand the connection between these black holes and the galaxies themselves. So what I'll say is that this image, which is the deepest image ever taken, is unfortunately kind of the limit of what we can do with the Hubble Space Telescope. You just can't do much better, given the detector properties and everything with the telescope itself, until you move to a new telescope. And so, of course, that's where the next frontier is coming. Here I'm going to just briefly talk about two very important facilities for these early universe studies. The first is the James Webb Space Telescope, which is hopefully getting launched next year. And the James Webb is basically the follow-up to Hubble. It is about 3 times the size of the Hubble Space Telescope. For those of you who've been to Chile, it is the same size as our current Magellan telescopes. It's a 6.5 meter mirror. But that's already 3 times bigger than the Hubble. But perhaps more importantly, the James Webb Space Telescope is optimized for the infrared, which is very important to study these very, very distant galaxies. And so this telescope really should be able to identify, hopefully, the very, very earliest galaxies, push back even further than those ones that Evo and others are finding. Now, that'll be really interesting, of course. But to really understand these galaxies, we need follow-up observations from the ground. In fact, this is equally important. In particular, we need to do spectroscopy. That is, we need to take the light from the galaxies and dissect it and understand it in detail. And that requires much bigger telescopes to do that. And so this is one of the primary drivers for, of course, the Giant Magellan Telescope, which we are building in Chile at our Las Campanas Observatory. Here's a nice little video for those of you who haven't seen this new video. And this telescope, most of you know a lot about this telescope, I think, because we've been talking about it for a while, is effectively a 25 meter or 80 foot telescope mirror. This is a tremendous jump from where we are today. And this telescope will allow us to study those distant galaxies in extreme detail. To give you an idea of the scale here, I mean, the dome is about 24 stories high. This is a huge, tremendous facility that we hope is coming online sometime here in the mid to late 2020s. And so it, combined with the James Webb, will be really able to understanding these early galaxies. Okay, so you've heard a lot. I hope you've heard a lot. My internet keeps saying internet unstable, so I'm hoping I'm not talking to myself and the dogs.
You're not.
And I'm sorry I talked a little fast, but I wanted to make sure I got through things. And but I hope what you've learned here is that what I would say the legacy of the Hubble Space Telescope in my mind is that it really has allowed us to study the universe. I didn't say this, but the range that Hubble allows us is basically 97% of the age of the universe. We can cover 97% of the universe is studyable with the Hubble Space Telescope. And the next generation will get us those last 3%, hopefully. And that'll be really exciting. And I look forward to talking to you more about that. And I'm happy to answer questions. In the meantime, let me just say, I hope everybody's doing well and staying safe. And we'll continue to call in for these future talks that we have with some amazing scientists coming up in all of our departments. Thank you.
Thank you so much, John. We really appreciate this. And thank you to all the attendees. We have 600 people listening between Zoom and so that's fantastic. Sorry, we got off to a little bit of a late start. We were having some technical difficulties, but we have a ton of questions. So let's get started with those. Sure. I'm going to try to synthesize some that are similar so we can get to as many people as possible. We have a number of questions about dark matter. Particularly, which is a subject near and dear to Carnegie's heart. Particularly people are interested in what's the breakdown between dark matter and dark energy in the makeup of the universe, and also, do we have dark matter in ourselves?
Yes, and so that's a really great question. So I will answer certainly here, but if people want to know more about dark matter, I gave a talk as part of our Huntington lecture series in Pasadena in February, and that is online, and there's a huge segment in that talk about dark matter, really to understand why we believe in dark matter, because it is I know a lot of people are very fascinated by it. We're all fascinated by it. But of course, it's a challenge because it's been 40 years since Vera Rubin's big paper came out. It'll be in 1980. And so we've known about dark matter, and even before that, there was evidence of it. And it's a bit challenging that we haven't, of course, figured it out yet. And so I talk about a lot of that in my Huntington talk, so please find that on the Carnegie website for more information on that. What I'll say is that if you look at the energy distribution, the matter energy distribution of the universe, the dark energy is about 75%. It is the dominant force. And dark energy is the force that is accelerating the universe. And we know even less about dark energy than dark matter. The dark matter itself is another 20-something%. And the real material, I shouldn't say real material, the baryonic material, the material that we are made of, is just a few percent of the universe. And so it is always important to remember that when we look at these images of the galaxies, you're seeing the baryonic material, you're seeing the atoms. And that is only about 4% of the stuff in the universe. And so astronomers basically have to use that 4%, which is what we can actually detect via telescopes, to try to imply and infer what else is out there, the other 96%, which is the dark matter and dark energy. And so the answer about dark matter, yes, dark matter is everywhere. It's not stuck inside of you. Dark matter, the thing about dark matter that makes it so challenging is that it doesn't interact with regular matter very well. This is in fact why it's so hard to detect. If it interacted with the atoms, for instance, there would be light signatures, or there'd be other ways of finding it that would be much easier than what we have to try to do. And so it is true that it is basically everywhere in the universe, but it isn't really interacting in that sense. I hope that makes sense. Does that answer that question? If somebody still has a question, feel free to let me know. But I think I've answered it.
I think you covered it. And I think we have a number of questions about a subject near and dear to your own heart, which are about X-ray astronomy, and specifically what does X-ray imaging bring to teach us that other kinds of observing don't?
Yeah, so I'm actually trained as an X-ray astronomer. I often say I don't know how an X-ray astronomer ended up running an optical observatory, but I actually know how. What happened was I was an X-ray astronomer as a graduate student, and then I came to Carnegie as a postdoc and learned to combine the two in a way that very few X-ray astronomers do. A lot of X-ray astronomers just work on X-ray astronomy, and traditionally a lot of optical astronomers would do that. And a lot of my work actually combines the two, and you learn a lot. So I would say, X-ray astronomy, there are kind of two major sources from the brightest X-ray sources of the sky. Let me start there. Are these accreting black holes, which I talked about. And so they're really interesting, of course, for that reason. The other source is just very, very hot gas. And by hot gas, I mean, it has to be 10 to 100 million degree gas to produce a lot of X-ray emission. And we do see that gas in the most massive systems, these clusters of galaxies I talked about earlier. And that was one of the things that I worked on quite a bit for my thesis. And that gas is an interesting probe of dark matter, it turns out, because you can use the temperature to actually gauge how much matter must be there to get the gas to that temperature. Because the gas that you see in a cluster is basically reflecting the gravity. So it's a kind of an independent, somewhat independent way of inferring the presence of dark matter. And so for me, X-ray astronomy, those are the two biggest contributions. But just like the Hubble, as I said, the Hubble Space Telescope has an impact in every field. X-ray astronomy has impacts in lots of fields. It turns out that comets actually produce a little bit of X-ray emission for reasons we don't fully understand and various things. So almost every field is impacted by it. But I should say X-ray astronomy has to be done from space, because thankfully the Earth's atmosphere absorbs X-rays. Because if it didn't, we wouldn't be here. We would be fried. And so all X-ray astronomy, it's much more difficult, and it has to be done from space. And so the Chandra X-ray telescope I mentioned for the black holes is in fact kind of the cutting edge instrument in that field right now. I'm part of a team that is actually proposing a new follow-up to that. It'll be kind of the James Webb Space Telescope of X-ray astronomy in a sense, called AXIS. And that has gotten very positive reviews from NASA, and we hope that telescope will be online by the end of the 2020s. So that'll be very exciting.
That's fantastic. And it leads in perfectly to a couple of questions that we have about space telescopes, and particularly how they are protected from radiation, from meteorite impacts, and also how they get modified and updated.
Yeah, those are lots of questions there. So the question about radiation is actually important, particularly for certain sorts of detectors. And often in the case of some telescopes like the Chandra X-ray telescope, the detectors have been significantly damaged by radiation. These are electronic devices similar to the ones we use are charge coupled devices similar to the ones we use on the ground, kind of a fancy version, an X-ray version of the camera on your phone in some sense. And they are susceptible to damage from, for instance, big solar flare activities and things of that sort. And so one of the things we do is the orbits of those telescopes are designed usually to avoid areas where they would come in contact with a lot of radiation, and or that you basically cover the telescope up. You put literally a cover on it so that you aren't introducing the instruments to the radiation during those peak times. So there's a lot of effort there. In terms of meteorites, there is probably some damage that happens from small meteorites. I think we all have this vision in our head that when you're flying around space, there's a lot of space rocks. Space is remarkably empty. I mean, there's of course a chance that would happen, but the chances are actually pretty slim. And a lot of the structure of the telescopes itself are designed to withstand small impacts. But obviously an impact with a bigger rock would not be good. But so far we've been pretty lucky there. And what was the other part, Natasha? Let me see.
How does the Hubble Space Telescope get updated, or other space telescopes?
Oh, updated, yes. So the answer is, unfortunately, most of them do not get updated. The Hubble was really quite lucky. The Hubble is in low enough Earth orbit that with the shuttle program, it could be, as you probably all remember, there were various repair recovery missions. And in fact, there are, I think, 5 of them. And every time they did that, they could actually take out the instruments and put in new instruments. Now, that's no longer possible because the shuttle program doesn't exist. And so right now, the Hubble, the last one was in 2009, I think. And basically, the Hubble is still working, but at some point, as the instruments die, it won't be possible to replace them. But the other ones like the Chandra telescope and James Webb will actually be in a dark spot very far from the Earth. They're not repairable. And so this is one of the challenges. Hubble was originally supposed to last no more than about 10 years. And the repair missions have extended it to now 30 plus years. But like James Webb, that's unlikely to happen. Most likely it will, at the end of its 5 or 10 year lifetime, it'll be over. And that's just something you have to live with. Right now, we just don't have a way of repairing them. This is, of course, a huge advantage for ground-based telescopes where we can update our instrumentation all the time, and we do. And it makes the telescopes more valuable over time.
Perfect answer. So we have a number of questions about black holes, but I'm going to read one out because it's very entertaining.
Uh-oh.
Question from Stefan, which asks, why haven't black holes in Pac-Man-like fashion captured all of the matter in the universe and then captured themselves?
Yeah, that's a really great question. So this is another common misconception about black holes, that so black holes have extremely strong gravity very close to the black hole itself. But if you move not even that far away from it, basically it acts like a normal gravitational body. So for instance, if you were to take the sun and scrunch it down to something very, very tiny, you could actually create a black hole from the sun. But if you did that, the Earth would continue to orbit as it does, because we're far enough away that the gravitational effects of the black hole really would not be so powerful. You have to be very, very close to the black hole to see those effects. And so I think, once again, in movies and things, it kind of appears that the whole universe is getting sucked into these black holes. They really don't act that way. If you're really close, you're in real trouble. But once you move a little bit away, they act like any gravitationally bound body. And so they're massive, but they're not, even the ones that are 1 billion solar masses, that's a pretty big object. And if you come near a supermassive black hole, you're probably going to be in trouble. But for the most part, stars far away, we're very far from our supermassive black hole in our Milky Way, and we're not really impacted by it at all. So don't worry. There are many more things to worry about.
I just like the image of Pac-Man going through space, swallowing everything up. So we have a few questions about the age of the universe and can we see all the way to the edge of it? So I'm glad somebody asked this because I meant to point this out and I didn't really point this out. I should have. So we know the age of the universe remarkably accurately, I would say. It's about 13.7 billion years old. We know that from multiple ways. But perhaps the best way is we can see the remnant radiation from the Big Bang, and this is visible as light at millimeter wavelengths, and it's called the cosmic microwave background, microwave wavelengths. And based on modeling of that, we can trace back the timeline pretty accurately. So the timeline of we know the age of the universe really well. As I said, like 13.7 billion years old. The reason why I meant to mention that earlier is because when I was saying, for instance, Eduardo's black hole or Evo's galaxies that they're seeing over 13 billion years in the past, they're seeing objects within the first billion years after the Big Bang. That's why it's so impressive, to me at least. And so the answer is we can see back to that, the farthest back we can see is that cosmic microwave background radiation, which is about 300,000 years after the Big Bang. It's not all the way back. We can't really see beyond that. In terms of galaxies, the farthest back we can see are still several 100 million years after the Big Bang. So we don't really see all the way back to the very first galaxies yet, but that's what we will do with James Webb and the Giant Magellan Telescope. And so we have time for one last question. Unfortunately, we can't get through all of these, but anyone whose question was not answered, if they want to submit it in email to events@carnegiescience.edu, we'll make sure that John or someone from our astronomy staff will answer that question for you. So we're going to have one last question, and then after John answers it, then our president, Eric Isaacs, will give some brief concluding remarks. So this is another cute question to close with. It's from D. Ellison, and it says, how in the world do you learn how to be an astronomer? It's amazing to me. Thank you so much for this great presentation.
Oh, well, thank you. What was the first part though? How did we what?
How do you learn to be an astronomer?
Oh, how do you learn to be an astronomer? So that's a great question. So I'll say that I've met two kind of different types of astronomers, and this is being, of course, very general here. There are astronomers like myself, which I always say I was born to be an astronomer. And what I mean by that is I was into astronomy from the very earliest ages. When I was 5, one of my first memories is actually is seeing a solar system model in my kindergarten class. In fact, I can't really think of anything before that, and it's a weird first memory, but that is my first memory. And my mom, who was a teacher herself, she was a 4th grade teacher, recognized very early on that I was interested in science and astronomy in particular, and she bought me books because, of course, the internet didn't exist. But she bought me books and just kept buying me books. And by the time I was 7, I ended up getting my first telescope. And then I made my first telescope. I ground the mirror when I was 12. I was a hardcore astronomy geek. And so in my mind, by the time I went to UC Berkeley for undergraduate school, I already knew that's kind of what I wanted to do. But then there are other astronomers. Wendy Freedman, our previous director, is a great example. Wendy just was very interested in science and math. She was really great at it, obviously. And she didn't know what she wanted to do. And then she got to college and she took a bunch of classes, and all of a sudden astronomy caught her eye and she ended up becoming a famous astronomer. So I think that, but the thing you can do is when you're for parents who are looking at their children is, find things that they're interested in, expose them, especially in a time like now, where, of course, you're home with your kids a lot. There's a lot of great materials online in terms of videos and things that didn't exist, of course, when I was a kid, but reading and just kind of feeding their appetite for science. And I also like to point out that, the world doesn't really need 1 billion astronomers. There aren't very many of us. We're a pretty rare breed, actually. Doesn't mean you shouldn't be an astronomer, but there's, of course, many ways you can play a part in astronomy without actually being an astronomer. So at Carnegie, we, of course, have engineers. We have people who help build our instruments. We have people who run our telescopes, all sorts of jobs that are tech related, computing modeling, and all sorts of things. These all play a really important part in astronomy without actually having to be an astronomer. To be an astronomer, you need a Ph.D. to really be a professional astronomer in any sense at all these days. And I guess the only other, I don't remember what I was going to say, something else, but I can't remember. So anyhow, like I said, for me, I was kind of born to be an astronomer. And of course, it's hard for me to imagine doing anything else. It was just like, it's a dream come true for me to be an astronomer and then running an observatory, a place like Carnegie, where we have really some of the best facilities in the world. I mean, I never would have imagined that. Even, this is another side thing, but when I was applying for postdocs, I spent 5 minutes on my application to Carnegie because I was convinced I had no shot as an X-ray astronomer, particularly, at getting a job at a place like Carnegie. That's how impressive the Carnegie Fellows are. And those of you who've met our fellows, you know this. And we get hundreds of applications for a single or for two or three jobs. And I had convinced myself there was no way they were going to hire me. And here I am 26 years later. So you never know. Thank you so many people, 417 participants. That's really amazing. I hope you're actually
another
listening.
100 on YouTube.
Excellent, good. Well, this is great. This is really great. I have to say, preparing for this talk was extremely difficult for me because it's the first time I've had to do a talk like this. And it's hard not having the audience. I like to be able to interact with the audience. So I do hope people got things from this. And if you have comments on how we can improve it, please let us know. Let me know, or let Natasha or Eric or somebody know. That's it for me, unless I have more questions. Eric Term, I think.
Okay, John, thanks so much for a terrific talk. I also really appreciated your personal story about your personal journey about how you became a scientist, and I hope people take that to heart with their kids, with their friends, their relatives. It's a great endeavor, and Carnegie's a great place to do science. So I also wanted to thank the audience. This, as John's already said a couple times, this turnout was more than we could ever have hoped for and expected. Over 500 people, including everyone who came in from different paths. So thanks so much. I really hope you'll join us again a week from now, April 16th. We're going to hear from one of our earlier career scientists, who's an evolutionary geneticist, Moy Esposito Alonso. He does some really cool stuff. He investigates how weather and how plants will evolve to keep pace with climate change. And he does this through a large-scale ecological experiments as well as genome sequencing. So I think you'll find a very different kind of science, but also equally exciting and incredibly pertinent to the world today. We plan to have these programs at least every other Thursday afternoon. Of course, this next one is a week later, but every other Thursday afternoon, each one will be as exciting, hopefully as exciting as what John just did for us. And I want to thank you again for taking some time in your afternoon. I know this is a difficult time for everybody, but thank you for taking the time to join us on this type of programming. We really look forward to welcome you again next week and then in the weeks to come. And hopefully we'll see this end pretty soon and can get back to our laboratories and our observatories. But until then, we'll continue to communicate with you in this way. So thanks again, and we'll look forward to seeing you.
Thank you, everyone, again. And as a reminder, if your question was not answered, please feel free to submit it to events@carnegiescience.edu, and we'll make sure you get an answer.